Hi, everyone. Welcome to Pinterest Lab's distinguished speaker series. My name is Jure Leskovets, and I'm Chief Scientist at Pinterest. I'll be your host for today. We tend to organize these talks at Pinterest open to the public once a month, where we invite leading researchers from academia as well as industry to tell us what are exciting new technologies and what exciting things are happening in the academia. And generally, we tend to talk a lot about machine learning and AI and user modeling, computer vision, and so on. But we also touch on large-scale data processing systems from time to time. And today, I'm super excited that we are able to welcome Semih Salihoglu, who is an assistant professor of computer science at the University of Waterloo in Canada. And his research focuses on developing systems for managing, querying, and performing analytics over large-scale graph structure data. And today he's going to talk about his ongoing projects, including GraphflowDB, which is a graph storage and database engine, as well as I think about Graph Surge and some other projects coming from his group. Semih holds the PhD from Stanford University in computer science, and we overlapped in the department, and he also has a VLDB Best Paper Award from a few years ago. So the way we are going to do this is that Semih is going to give the talk. If you have questions, please enter them either into the chat or even better in the Zoom Q&A feature. And I'm then going to read your question for Semih to respond. His talk has about 3 parts, so we will do some questions in the middle and majority at the end. So thanks again for attending, and Semih, the floor is yours.
Right. Thank you very much, Jure, for that introduction, and thanks everyone for coming to my talk. So when Jure invited me to give a seminar, he asked me to talk about graph databases in general, and also particularly about GraphflowDB, which is a graph database management system that we're developing at University of Waterloo in my group. So I'll do exactly that. I'll tell you about graph database management systems, briefly covering their long history, tell you about what they're good at, what they're designed for, and then later talk to you about some modern query processing techniques, some novel query processing techniques that we have been integrating to GraphflowDB, and tell you about the benefits that we get from those techniques. Right? So before I start, let me tell you a little bit about the broad research that we do in my group at University of Waterloo. So I'm a core database researcher, and I work on developing software systems to manage and process, in particular, graph structured data. And in the market of graph processing systems, there's really 4 classes of systems. So, and we maintain in my group interest in all of these four types of systems. So the first one, which is the topic of the seminar, is graph database management systems. GraphflowDB falls under here. And as I'll try to articulate in this talk, you should really think of these class of systems as relational database management systems that are particularly optimized for what people refer to as graph workloads. And those are workloads that have a lot of end-to-end, many-to-many joins. And I'll tell you a lot more about that throughout this talk. The second class of systems are RDF systems. So these are systems that are particularly designed to manage what are nowadays being called as knowledge graphs. So a knowledge graph is effectively a set of facts about real-world entities. So a fact could be something like Justin Trudeau is married to Sophie Trudeau, and that could be represented as an edge between 2 nodes. And a set of such facts can be seen as a knowledge graph. And RDF systems, although they have a lot of similarities with graph database management systems, as well as relational database management systems, they're particularly designed to manage that type of knowledge. A third class is a very broad umbrella class that I'm calling graph analytics systems. And within my group, we're actively developing a system in this space called Graph Search. And these are systems that are particularly designed to do some kind of batch processing. So maybe a very long-running, say 3-4 hours running page rank computation, ranking computation, or a clustering algorithm, or maybe a training a graph neural network model. I'm putting all of them under graph analytics systems. And I had developed one such system during my PhD years called GPS, and another one is Graph Surge. that is being developed right now in my group, which leverages a very interesting technology. Unfortunately, I won't get the time to talk about it, but it leverages a technology called differential computation for graph analytics. But I'm happy to talk about that offline or in the Q&A. And then the last class is an important class called graph visualization software. And we do have a smaller project in this space called GraphWrangler that's partly a visualization software as well as an ETL software, right? So that's the broad market of graph processing systems, and we do maintain interest in all of these four. Okay. So before I move on to talk about graph database management systems, I want to put a plug-in for a paper that we wrote. This was led by one of my PhD students, Siddhartha Sahu, where we did a very extensive user survey of graph technology, asking 89 users and then 10 in-person interviews of what kind of graph technology people in industry use, what kind of graph data they have, what kind of computations that they do, what are their main challenges, and so on and so forth. So if you're broadly interested in this market, in the space of software systems, I highly recommend this as a non-technical read. It did, for us at least, highlight several important trends from the users that has been actually influential in driving our research. So let me start with a one-slide overview of what graph database management systems are. So graph database management system, in one sentence, they're read-optimized database management systems that are designed for read-heavy workloads with large many-to-many or end-to-end joins, right? So to give an overview of any database management system, there are three main components of database management systems. There's the data model, the query language, and actually the actual system implementation. So let me give you a very high-level overview of these three components for graph database management systems. So the data model is what is known as property graph model, which is really a labeled graph. So as an application developer, suppose you're developing a recommendation algorithm or a fraud detection application on top of a graph database management system, the way you model your data, your records, is as a set of nodes, labeled nodes, and as a set of labeled edges and arbitrary key value properties on these nodes and edges, right? So that's the data model, compared to obviously a relational model where you would represent your data as a set of tables. The query language is what I call graph-specific SQL. So the query languages of these systems are meant to be very similar to SQL, where, for example, this is a snippet from the Cypher query language of Neo4j, which is one of the leading commercial systems in the space, where the joins where in SQL would be represented in the from clause. Instead, in Cypher, they're represented in the match clause. And there is graph-specific construct. So to represent your joins, you actually draw a subgraph pattern instead of in SQL, you would represent a sequence of tables. But then there is also, you could do projections and aggregations in the return clause and filters in the where clause, very similar to SQL. Now, it's very difficult to say something very broad and universal about the system implementations, but it's fair to say that a lot of them will have some kind of graph-specific storage. For example, universally, they'll all index their graphs, their data as in adjacency list format or a variant of adjacency list format. And in terms of the query processors, they're designed to do what people refer to as fast traversals, which in relational sort of terminology would refer to nested index loop joins, meaning using the adjacency list index, you can move from one node record to its neighbor records very quickly, right? So that's broadly what graph database management systems are. Okay, so I'd like people to keep in mind this end-to-end join as a workload sort of that's typical for graph database management. So the applications that are being built on top of these systems contain a lot of end-to-end many-to-many joins, right? So if you look at the internals of these systems, again, you'll see they're very similar to relational systems. So for example, you will see a lot of operators that implement relational algebra operators like joins, projections, aggregations, selections. They'll have cost-based optimizers like relational systems do. So there's a lot of similarities with relational systems, but there are also several differences. Aside from the data model and the query language, there's also at the system level some common differences. So let me tell you what I think are the main three differences that I observe between graph database management systems and relational database management systems. So the first one is what I'll call as predefined and pointer-based joins versus value-based joins in relational systems. So graph database management systems, they are designed to perform a set of predefined, a restricted set of joins, but they're designed to be very fast at those joins, okay? I'm using the term predefined because this was a term that was used by Ted Codd, the inventor of the relational model, to criticize the graph database systems of his era, which was basically the systems that were built, the IDS system and the ones that were built on IDS. So IDS, for those of you who don't know the history of database management systems, was the first database management system in history, developed by Charlie Bachman, based on a model called network model. Network is another term used for graph. It was basically a graph model. And Ted Cott, 10 years later, when he came up with the relational model, was criticizing these systems by saying that, look, in the relational model, you could join any two tables on arbitrary two columns as long as they have the same data type. Maybe those two columns have string data type. Whereas in the graph, in IDS system, you could only join a node record, a record with other records only if you had predefined to the system that those two records were already linked through an edge. Okay, so this distinction nowadays in the contemporary graph databases don't exist as strictly. So graph databases can join arbitrary node records with arbitrary node records, but it's still fair to say that graph databases are particularly optimized for these predefined joins, so which you can think of them as pointer-based joins instead of value-based joins. So it's restricted in that sense, but it's also what makes them very fast exactly at those joins. Okay, so that's one, and I think the most important difference between these two classes of systems. The second is that graph database systems have semi-structured data model, so they're more flexible. What that means is that when you ingest data into the system, you don't have to specify the type of every piece of data, which is good for several applications in it, like data integration, and they have better support for variable length recursive join queries. So for example, suppose you had a financial transaction network of accounts and transfers between accounts, and you were interested in the following question: give me all direct or indirect possible sources of money into Alice's account from Canada. There's a very easy way to write this in a language like Cypher, where it's quite self-explanatory. A transfer star B really says that direct or indirect transfer edges from a node A to a node B with some predicates. Certainly doable in recursive SQL, but objectively harder. A lot of users really don't like writing or find hard writing such queries in recursive SQL. Okay, so these are, I think, the three primary differences in terms of the features that these systems support. So before moving on to the technical part, I'd like to leave you with several excellent links about the graph database systems and their long history for those who are interested in the birth of our field. So the first paper that I want to link to is Thomas Hay, who's a CS historian, has an excellent paper recovering, giving an overview of the birth of database management systems. And this is essentially an image from his paper, but it's originally a drawing from 1962 of the IDS systems model. And the graph, I hopefully is very clear, where there's node records and essentially links between node records. The second two links are Bachman's and Turing. They're both Turing Award winners. Their Turing Award lectures are, I think, very interesting to read, to see the design points that they were coming from when they were developing these two different classes of systems and starting essentially this never-ending division between database management systems that are based on graph models and based on the relational model. And another link is Bachman has 40 years later has a very interesting talk where he essentially remembers the history of developing the IDS system, what kind of features they were interested in, what their design point was, which is at parts also amusing because he's a Turing Award winner, but he's one of the few who doesn't have an academic background. So he recounts the story of how he didn't know who Turing was when he won the award. And he does some research and finds Turing mother in England and they have tea. So there's several interesting historical stories that you might find amusing for anyone who's intellectually interested in the birth of data management. I highly recommend these as very entertaining reads. Right, so in one slide, let me tell you about an overview of GraphflowDB. So GraphflowDB is an in-memory graph database management system. It supports the property graph model that I talked about and the OpenCypher query language, which is the open source version of the Cypher language of Neo4j. It's designed to have two primary features. First is it's designed to be very fast on many-to-many joins. And to this end, we have been integrating several techniques, which are interestingly techniques that were originally designed for in the context of relational database management systems by theoreticians in the community. But as I'll try to articulate and argue, I think they find some of their best applications in the context of graph database management and the workloads that graph database management support. And the second feature that we're going for is scalability. So we have highly compressed in-memory columnar storage optimized for graphs. We have papers on all these features that I'm talking about. And today I'll talk about two of the query processing techniques for end-to-end joins, factorized database and worst case optimal joins. Right, so that's going to be the focus of this talk, and I'll give links to the rest of the work that we've been doing on the system. All right, so this is the end of the first part of my talk. So the next two parts, I'll give you overviews of these two query processing techniques, factorized query processing and worst case optimal joins. Right. So let me start with factorized query processing. So as I said, graph database management systems, they're read optimized systems. They're designed for end-to-end joins. In the relational market, the read optimized systems are columnar RDBMs. So systems like Vectorwise, MonadDB, or Vertica, these are also systems that are optimized, they're read optimized, and they're optimized for a workload that we call all-app workloads. And I'll give you an example query in a second, but these are also read heavy. So they read large chunks of the database when you answer queries. But the joins in these queries are not many-to-many. They're often primary foreign key joins. And these workloads are often aggregation heavy, okay? So the way traditional query processors that are designed for these workloads in columnar RDBMSs is that every physical operator in the system that implements a particular relational algebra operator, obviously, is going to process on a block of flat tuples at a time. Okay, so let me give you an example. So suppose this is your query that is essentially asking for, give me the average age of employees in each department, so group by department, but only considering employees over age 30, right? Over an employee table. And here's a very simple plan for this, probably the standard plan for this, where your scan operator is going to scan a block of tuples from the employee table. And then in a tight loop, because there's a filter on the tuples, it's going to run the filter of age greater than 30, marking each tuple whether or not they pass the filter, right? Then once this filter has happened, it's going to pass this block of tuples to the group by and aggregate, which is also going to do a block at a time processing, right? So the fact that processing happens block at a time is very good for CPU utilization. This is very well understood, compared in particular to even more traditional query processors that perform tuple at a time processing. But the fact that a single block of flat tuples is passed between operators is not really optimized for end-to-end joins. So let me show you what the shortcoming is in the next slide. Now consider this query in the context of graph database management systems. So let me tell you what the query is asking. It's asking for two paths. Again, let's think of a financial transaction network where the account, the B node is owned by someone named Liz. And the A node is an account from United States, and the C node is an account from Canada, right? And here's an input graph on the right that I'm showing. So it's basically asking, the query is asking for money flows that Liz's accounts might be facilitating between United States and Canada, right? And here's a very simple plan from, say, GraphflowDB or Neo4j. It's going to look very similar to this, where we'll scan the B nodes to find the accounts owned by Liz, and extend is the join operator in graph database management systems that will use the adjacency list index to extend, in this case, B tuples to AB tuples and AB tuples to ABC tuples. Okay. So the scan, if you were to adopt traditional block-based processing, you would get a list of B nodes and read its owner properties, and then run in, again, a tight for loop, a filter to find the accounts owned by Liz. But by the time you come to the last operator, the output of this block would contain a lot of repetitions because of the nature of the many-to-many relationships in the data and the query. So, for example, in this example that I'm showing, the node L1, Liz's first account, has got 100 input neighbors from United States and 100 output transfers to accounts in Canada. So it's part of essentially 100 times 100, 10,000 tuples, 10,000 paths, two paths, if you will. Okay, so that inevitably leads to a lot of data repetitions in the intermediate data that's passed between operators. Okay, so B is going to be repeated, the owner value will be repeated, so on and so forth. The A values will be repeated, right? And this is inevitable, and it happens because of the restriction of passing a single group of vectors or single group of tuples that are flat. And the solution to this is instead of representing the data, these intermediate relations as a set of flat tuples, is to represent them in what are known as factorized representations. Okay, it's essentially to change the representation system of the tuples. Okay, so this is essentially the theory of factorization, developed these representations. This is a theory that was developed by Dan Altanu, who used to be at Oxford University and now at University of Zurich. So there are two types of factorized representation systems I'll talk about. The first one is called F representations. So the output of the previous query, which in my example contained 20,000, essentially two paths. Okay, each Liz account was part of 10,000 in my example data, would be much more succinctly represented as not as a set of flat tuples, but as essentially unions of Cartesian products as follows, where the Cartesian product would be, for the first 10,000 tuples, would be its L1 Liz for the attributes B and owner, Cartesian product with the 100 neighbors, incoming neighbors of L1, Cartesian product with the 100 outgoing neighbors of L1. Okay, unioned with, similarly, L2 Liz, Cartesian product with 100 neighbors of L2 and 100 neighbors, outgoing neighbors of L2, right? It's a much more succinct way to represent the same relation in a different representation system, avoiding the value repetition problem that I talked about, okay? Now, in general, if I gave you an arbitrary relation, there is no reason to hope that you can find a good factorization. It's computationally hard. But if the relation is the output or an intermediate result of a query Q, then we can find good factorizations of the relation by analyzing the conditional independence of the variables in Q. So, for example, if you look at this, this was the join part of my query, ABC. You can see in this query that once B is fixed, that the set of A's and C are independent. That's because there is no further join predicate between A and C nodes. There's nothing joining A and C. And in the where clause of my query, there was, again, nothing that was depending a property of A with a property of C, let's say. Okay, so they're actually completely independent, right? And the way we have integrated an F representation-based processor is to, instead of passing a single block of tuples, we pass essentially multiple groups of tuples, which we call list groups, to represent these set of relations as in an F representation. So let me sort of demonstrate to you and simulate to you how processing of the previous query would happen in our F representation-based processor. So I'll have exactly the same query plan, and the scan operator, as usual, is going to read a block of nodes and the owner properties of those nodes and run the filter in a block-oriented manner. But this first block of tuples is also going to have a field called the current index, which could be -1 or it could be a positive number, and I'll describe what that means in a second. So when it's -1, it means that all of these tuples are alive for a meaning that will become clear in a second. So these block of tuples would be passed to the extend operator, and the extend operator is going to do two things. The first thing it will do is that it's going to, because it's extending the B values, and B values are in a list group that are not flat yet, it will flatten that list group by setting the current index to 1, which conceptually just means that now only the first tuple in this block is visible, and it's being passed between operators. And then it's going to add a new list group, which is going to be the incoming edges of L1, which is the tuple that is alive from the first list group, right? So this represents essentially the Cartesian product of L1 with these 100 A values, and that's going to be passed to extend C, which is going to again extend B, which is already flat, to its outgoing neighbors. Okay, and this will be sent in this factorized F representation manner to, if this is the end of the query, it will be sent over the wire to the client of the database, right? When it's pipelined, so when the processing goes back, A is going to now increment the flattened list group to the second tuple in the list, and going to extend the second L2 node to its incoming neighbors, and then pass this to the C, who is going to extend it to the outgoing neighbors of L2, which will be sent again to the client, right? So let me just show you what kind of sort of performance gains you could expect when you move from a flat-based representation to a factorized F representation on a micro benchmark. So this is a micro benchmark that we are using to evaluate these benefits. And I have three different very classic sort of queries, 1, 2, and 3 hop path queries, where I have two versions of the queries. The filter versions of the queries look for some k path with the last edge is going to have a predicate, and then a count version of the queries where we're just going to count the number of paths. And I'm running it on a LDBC social network benchmark. So this is a benchmark that is slowly becoming the TPC-H or TPCC of graph database management systems. So for those of you who don't know, TPCs are the most widely used benchmarks for relational database management systems, and another social network Flickr data set. And I'm comparing the performance of GraphfLow with flat representations and GraphfLow with F representations. So the red lines here are the performance gains of using the F representation-based processing. And as you can see, you can get between 1 to 2 orders of magnitude improvements just by, by adopting this F representation-based processing. I'm not a big fan of system-to-system comparisons. They get a bit unscientific because systems, they change, a lot of components change, but there's even much larger differences of these runtimes that I'm showing with 3 baseline commercial systems that you can find in our paper. This is a paper we put less than a month ago on archive that you can see. Right? So that's one representations, factorized representation system called F representations. Now, F representations do not capture every possible value repetition. So let me show you a shortcoming of F representations. So I'm changing my query now, and my query is a bit finding a longer path. Now it's looking for three paths, where this is essentially looking for a 3-step money flows, if you will, from US accounts to Canadian accounts. So A's are accounts in US, these should be these are accounts in Canada. And in my example graph over here, I got a bunch of unrelated data, but the nodes that are blue are from the US and nodes that are red are from Canada, right? So now when you look at a query like this and the example data that I'm showing here, you can immediately observe that this really, all the paths that this query is searching can be found in this subgraph. Okay, that's the most compact way you could represent that output. Okay, that's really the relevant subgraph that contains all the paths. Okay, there's a lot of paths if you kind of flatten them, but that's really the core part, core subgraph that contains all the answer. Okay, but if you do an F representation based processing, right? Let's take a very perhaps the most obvious plan that a system would use for this, where because there's a predicate on the A nodes, we'll start by scanning the A nodes, and we're going to extend left to right from A to D. This type of processing would give you a final output that looks like this, where we're going to have 4 list groups, but really the only factorization benefits that we're going to get are going to be a little bit from the last D node. So A values have to be flattened because extend B needs to flatten them. B needs to flatten because extend C needs to flatten them, and variable C's need to be flattened because extend D needs to flatten them. So you get a little bit of benefit from the last extension. But if you look closely at this relation, you can see a lot of repetition. So for example, all the subpaths that start with C2 are repeated. For example, these are essentially not the entire tuple, but they're parts of the tuples that are repeated. Or all the subpaths that start from B2 are also repeated. Okay, and F representations cannot capture that. It's because certainly, for example, A1 and A2 share all the subpaths that start from B2, but they don't share the ones that start with B2, B1, and B3. So you can't really take Cartesian products here, right? So that's a limitation of F representation. So what you really need is a way to group tuples into sets and point to them. Okay. And in the theory of factorization, that's done by another representation system called D representations, which stands for F representations with definition. So let me show you what that representation system would look like. So the same output of the previous query in F representation is this. The way we would form a D representation is that we'd first generate subrelations for all the subpaths starting from C's. okay, and we give them a name. So dnc1 here, which stands for d naught c1, represents the Cartesian products in F representation, c1 times d1 d2, okay? So it represents the two paths that start from c1, so on and so forth for c2, c3, and c4. Now, using these named expressions, we can represent all the subpaths that start from b1. So here, over here, b1 times dnc1, dnc2, essentially uses the named expressions that we formed previously, and recursively the final query, which would contain all the variables a, b, c, d, same schema as the original table, would use these named representations that use the subpaths that start from b values. Okay, so that would be the final output, which is which is more compact than F representations. Right. So again, just like F representations, it's hard, computationally hard to find good representations for arbitrary relations. But if these relations are outputs of queries, again, you can detect good groupings by analyzing the independence of variables in Q. Okay. And the second note that I want to make here is that if you look at this, so each row over here in this D representation corresponds to the out edges of a node. So for example, this row, A1 times dn B1, dn B2, essentially reflects that all the paths that start from A1 can be represented as A1 Cartesian product, all subpaths that start from B1 and B2, which are exactly these two edges. So the size of this representation is going to be commensurate with the amount of edges in this subgraph, which is exactly what we wanted. That's the most compact way we could have represented this, right? And the representations do really capture that. So our implementation of the representations or integration of this representation scheme into GraphflowDB is we will have essentially for each sequential pipeline, query pipeline in our plans, they'll optionally have a new operator called dgroup, which essentially construct the representations and cache them, which are shared with the extend or the previous join operators. So for example, the last D group over here is going to construct the D representations to represent all the subpaths starting from B values, it will be cached and shared with extend B, and we'll have DEX style plans where if there's a cache hit, extend can skip over large parts of the query, so to win a lot of performance and move, for example, in this case, to the last operator, the sync operator. Okay, and very importantly, still every operator that we have, every primitive operator processes a vector of values or a list of values, so we still get good CPU utilization as say the columnar systems in our GDBMSs do. Right? And just to give you a sense of, again, the performance benefits you could expect to move from F representations to D representations. Now we're taking an independent benchmark, LDBC social network benchmark. Queries over here contain short hop many-to-many joins. It's in a social network data looking for maybe 2-3 degree friends with analyzing maybe the posts and the comments that those friends make with predicates, certain aggregations. So this is an example query that would look for 2 degree neighbors of a node and the forums that they're part of, so on and so forth. And what I'm going to compare is the performance of our system under F representations and D representations, but using exactly the same plans. And again, on 5 of these, at least half of these queries from LDBC benchmark, you can observe significantly more than an order of magnitude improvements in performance. Again, those are on top of the benefits that we get from moving from flat representations to F representations. Okay. So I just want to end this part by giving you making the final remarks that
Semih,
yeah.
Can you go a slide back? We just have a bit of confusion about notation. So A dot something means it's an attribute of node A, but then sometimes you use this E, like E4 dot date. What does that mean?
So E4 is this variable that represents the edge between D and E.
Okay, so E
that's also a variable for an edge.
Mm-hmm.
So edges can have properties as well.
But if you say E dot country, then what?
E dot country would be a property of this node. So this is another variable I'm giving. Maybe I should have given this a different, or maybe this a different variable name. So E dot country would mean the country of this post node.
Okay, I think it makes sense. Yeah, I think it makes sense. I think the point is that these A, B, C, D are basically variables. They are
Exactly.
nodes, and then dot something refers to the attribute of that node.
Exactly. This is true for every graph language in general. Yeah. So you represent in your query, you give variables to nodes or edges, and then with a dot notation, you can access properties of those nodes or edges.
Thank you so much. And we think we discovered some typo on your slides that made everyone confused, but it's great. Thank you so much.
All right.
It's super interesting.
Okay, so let me just end this factorization part with some final remarks. So in my field of data management, there's been a never-ending quest by researchers and systems engineers who develop or work on database management systems with graph-based models. So be this the contemporary graph database management system or RDF systems, or the back in the day, the XML databases of late 1990s and 2000s, to come up with an alternative algebra to the relational algebra with operators that take in and output subgraphs. Okay. So every now and then, even nowadays too, in a conference like PODS or ICTD, which are where some of the more theoretical work gets published, there's going to be a paper that's trying to underpin the semantics of a graph query language, trying to define a graph algebra, but they've never been very successful. So I've never seen actually an implementation of such algebra in an actual system. And I think, part of the reason that I think most data management tasks really require relational algebra and relational operations on sets of tuples. But factorized databases, this factorization is a huge step in this quest, because as I tried to show you, when you adopt a system, a representation system like D representations, what's passed between operators are effectively subgraphs. They're representations of subgraphs. In our case, what gets cached are subgraphs. So, still, every primitive operator is relational, but still we can pass in very compact ways large sets of tuples, which are very similar to subgraphs. So that's what I want to leave with. And this is very important, I think, to improve performance. And GraphflowDB is certainly one of the first systems to take this idea seriously and implement it in an actual system, make it practical, and certainly the only graph database management system that implements these. And I think it's very important. And this is very important for the graph workloads, those with end-to-end joins. It's because this technique is really designed for end-to-end joins. This value repetition problem occurs with when there are end-to-end joins, many-to-many joins. Okay, so yeah, I have another about 10 minutes covering the second part. So Yuri, I could take some questions here about factorization if you see fit, or move on to worst case optimal joins. It's about 10 minutes, and then take questions.
I think we can move on.
Okay, all right. So factorization, that first technique that I described, is primarily improves performance on acyclic queries with end-to-end joins. But on cyclic queries, for example, click queries, most variables are all dependent. Okay, so you can't really factorize them. So every variable depends on everything. It's difficult to find good factorizations. And existing systems also do not generate very efficient join plans for cyclic queries. So let me tell you about the problems of existing systems on this triangle query that I've been showing. Okay, so first, I'll because the theory is in relational algebra, and I'll explain the theory of first case optimal joins in relational algebra. I'll just make a connection that these join subgraph queries can equivalently be represented as relational joins, as I've been trying to kind of implicitly make in the first part of my talk. So for example, the triangle query you could represent, this subgraph query, you could represent as a relational join as follows. If this is your input graph over here, you would give a relation name to each query edge in your query, R1, R2, and R3. So we're going to have three tables, R1 with columns AB, R2 with columns AC, and R3 with columns BC. And each table is going to be a replica of each other, containing each edge in this input graph as source and destination node. So the join of this is called a self-join, because every table is a replica of each other. So the join of these three tables is exactly the triangles in this input graph. So for example, this triangle is the join of these three records. So traditionally, take any relational database management systems in market right now, or graph database management system, the way joins are evaluated are in relational terms, table at a time, in graph terms, query edge at a time. So what that means is that if you gave this query to a relational system or a graph database management system, what will happen is that first, the system is going to join two of the tables, so maybe R1 and R2. It's going to generate a set of intermediate tuples. And as you can see, That intermediate table is effectively the open triangles in this graph, which will then be joined by the third table to close the triangles and find the final output. Okay, so there's a theory that essentially formally shows that these types of plans, what we call binary join plans, this type of traditional plans or traditional algorithms, they're probably suboptimal, primarily because these intermediate data that they generate can be really, really large. Okay, and this was made formal in the theory of worst case optimal joins, which started in 2008 with a Fox paper that observed and answered the following question. You might find this surprising. I always find this surprising that each time I talk about this, that this answer to this question was not known until 2008. Okay, very fundamental question. So the question is this: if I give you a set of n relations, R1, R2, and Rn, and I ask you, and I suppose each one has the same number of tuples, but I don't show you the tuples. All I tell you is the number of tuples, but not the actual tuples. And I ask you, what could be the maximum size of this join query? This was answered in a paper from Fox, which says, and don't worry about the formality here. It says that this bound, the size of this output could be the following: for each fractional edge cover, which I'll show you in a second, the output is going to be bounded by that. Okay, and this is a tight. So what a fractional edge cover is that you take the query graph in graph terms, you'll give values between 0 and 1 to each node, each edge, such that each node is covered. Okay, so in this case, A is covered because 1 plus 0 is 1. Covered means they sum up to at least 1. Okay, so this fractional edge cover gives a bound of n squared, but there's a tighter bound you could get, which is if you give 1.5 to each of the edges, which gives a bound of into 3/2, which is tight. Okay, that's called the AGM bound, or the fractional edge cover number of a query. Okay, so this was answered. And at the same paper, they also noticed that the traditional binary join algorithms actually can generate polynomially more intermediate data than this final output size. Okay, so they essentially detected the gap, but they didn't fix it. They detected the gap, they didn't fix it. So this was in 2008. So it took about like 4 or 5 years for the database community to come up with algorithms that close this gap, which is a little anticlimactic because it's essentially the second alternative idea you could have, most natural second alternative idea you could have to performing the join, which is instead of table by table joins, you perform column by column joins, right? Or in graph terms, instead of query edge at a time joins, you perform the join vertex, query vertex at a time, right? So the way these algorithms work, and I'm demonstrating one that's called generic join, is you're going to order the query vertices ABC, and what the system will do, what the algorithm will do, is that it's going to first find all A values that could be in the output, which is the intersection of these two columns. So, okay, 1, 2, 3 are the two possible A nodes that could have a triangle. Then it's going to take each A value and extend it to all possible AB values that could be in the final output, which is done again through intersection. So from this table, we take all the A values with 1. This table does not, it has B's, but it doesn't have A's. So we take all the B values. It's the intersection of those two, right? So on and so forth. This is done for each A value. And finally, each edge that was computed is extended to all the triangles. So the way that would be done is that we take all AB values and extend it to ABC values, essentially by intersecting, in graph terms, very natural, very intuitive, the outgoing edges of A and the outgoing edges of B. Okay, and that would give you the final triangles. Okay, so there's a theory that says that these are worst case optimal. What that means is that they will never generate more data than the AGM bound of the query. Okay, but it gave a very clear message. So this theory gave a very clear message that if you want to essentially close this gap for cyclic queries, you should perform the joins column at a time or query vertex at a time. So we wrote one of the first papers to actually take these ideas and integrate them into an actual database management system, into GraphflowDB, studying several questions like how should the query vertex orderings be picked. The theory is kind of oblivious to what the ordering should be, but in practice it matters a lot. For which queries should we use worst case optimal algorithms, worst case optimal join algorithms, because we also have a lot of expertise of making binary joins very performant. So for example, if you had a complex 8-cycle query like this, picking a pure worst case optimal join algorithm is not going to be very good, because you would do something like this. You would start with A nodes, extend them to AB, ABC, so on and so forth, until like that finds all the 6 paths, and then finally you'd get an intersection which could give you some performance gains, but you already found all 6 paths, and that's quite impractical. maybe worst case optimal, but it's not very good, you're probably better off finding the upper 4 arc and the bottom 4 arc and then performing a binary join. Okay. Then, we designed the dynamic programming-based optimizers that seamlessly mixes multi-way intersection-based joins, these worst-case optimal joins, with binary joins. So let me show you a couple sort of query plans from our system. So a logical plan for a complex subgraph query will look like this, where the top no box over here is the final query we're trying to evaluate, and you got two types of nodes in the logical plan, where some nodes have single child, and what that means, for example, this ABC means that scan AC nodes and then perform a generic join type of intersection-based join to match the triangles over here. Similarly, these BCDs are performed using generic join type of intersection-based joins. And then you got nodes with two children, which represent a binary join, and those are implemented with a hash join operator in the system. This is another plan. This is pure generic join type of execution, where everything is intersection-based. Okay, this would be called the one on the plan on the left would be what we call a hybrid plan. So here's a very interesting plan that I like showing. So this is a plan for the query at the top that seamlessly mixes these two types of join algorithms automatically. The system generates these plans automatically and actually often picks very good algorithms to evaluate complex subgraph queries, where on the left and right, we first find the ABC and CED triangles using worst case optimal join type intersection-based joins. Then we perform a binary join, followed again by another worst case optimal type join algorithm, intersection-based join. So we are seamlessly able to mix and generate these interesting join algorithms all together. So again, to give you a demonstration of the performance gains you could expect from this for cyclic queries, this is the hybrid plan. This is the plan that I'm showing over here on two different data sets. And I'm comparing against pure binary join-based plans. So you could, things that would take, maybe timeout or would take more than 5 hours can be done in a matter of seconds. And I'm also showing here a comparison with another system called Empty-Headed. This was a prototype system developed at Stanford by Chris Ray and Chris Eberger. Chris Ray is one of the developers of the theory of worst case optimal joins, where in their system, they had a much more restricted way of mixing these two types of join algorithms. And for example, in this case, they couldn't perform, they wouldn't mix these intersection-based and binary joins seamlessly. And their plans are, again, suboptimal. Right. So in the interest of time, there's a lot more experiments in the paper. This is a VLDB 2019 paper. I got links to this. In the interest of time, I'm just going to skip over this and just conclude. So for acyclic queries, so factorization, I think, is the key for gaining performance in the context of graph database management systems and relational systems. But because the workloads of graph database management systems contain a lot more end-to-end joins, it's particularly suitable for graph database management system. Similarly, worst case optimal joins, again, is designed for cyclic queries with end-to-end joins. It's a key to gaining performance. And my conviction is that these two techniques are key to making graph database management systems competent. So again, these were developed in the context of relational systems, but a lot of the workloads that relational systems support don't contain a lot of end-to-end joins. So it's not clear if these will, I think, see a wide adoption across relational systems, but I think it's going to be very critical for graph database management system. And I think, certainly we are one of the first systems to take these ideas seriously and integrate them and make them practical. And I would expect that over the next 5 to 10 years, they will see a much wider adoption across graph database management systems than relational systems. So I want to leave you with several references to papers we've been writing on the system, and several other references, particularly covering the theory of these two techniques. And I want to thank my students who do the hard work, and some of whom have graduated or moved to other system projects. And I'll thank you at that point and take questions if you have any. Thank you very much.
Thank you so much, Semih. This was excellent work, very interesting. We are open for questions. So if anyone would have a question, please type it into the Q&A feature of Zoom. You can find the button. to the lower right. But the first question we have is about what happens if your graph does not fit into memory, and what if you have to worry about distributed algorithms? What do you do in those cases?
Excellent.
How does query planning change?
Excellent question. So for worst case optimal joins, there has been several distributed implementations. Actually, one of them I co-authored with, if you're familiar with the timely data flow system of Frank McSherry, we implemented some worst case optimal join based data flows, which gets evaluated in distributed setting. And we have essentially techniques to achieve worst case optimality in terms of communication complexity. So when you talk about distributed computation, what you want to get across, what you want to achieve is some kind of guarantees about the communication complexity of your algorithm. So there has been several sort of distributed implementations, and we are not the only one. Several others have also developed some distributed algorithms. But for factorization, I haven't seen, and it's interesting what can be done with factorization. So that's I won't be able to give you a very good answer for how to sort of develop a distributed database system with that implements factorization. But so certainly for worst case optimal joins, our understanding has improved. So I can link to some papers, our paper certainly, and a couple other implementations on that. But something very interesting about distributed computation is that like graph processing in the distributed setting is generally hard. Like, and that's because it's kind of fundamental to the data, the fact that things are end-to-end joins and things can't be localized in a single machine. It's very difficult to achieve essentially good locality. So you end up essentially talking to every machine that you have in your distributed cluster. So it's very difficult to scale distributed graph computation. So we have, for example, in GraphfloW, we are in memory parallel, for which we have better ideas. And I haven't seen some very promising work for distributed graph database building. So that's an interesting area, but it's fundamentally difficult to do fast, efficient distributed graph processing, distributed graph data management, because the joins are end-to-end.
Okay, thank you. Cool. Next interesting question is about, could you comment, or is there related work on temporal queries from GraphflowDB, in a sense that, the question is, thinking about problems like finding the answer to what was the value of attribute X on node Y on the date Z. So that you basically, I guess, have nodes that have properties that change over time.
Yeah, so I think that part of temporal querying, of getting essentially multi-version of your node records or something, is not different than getting multi-version support, data support in relational systems. So I'm not sure of which systems have that feature, but there's nothing that makes the problem different in the context of graph database systems, I think, compared to relational systems, I mean. One thing interesting about, so if I were to sort of modify the question a little bit, when you talk about temporal queries, a common class of queries are continuous queries. So things like, as the graph is changing, I don't want to find all my triangles. I just want to find, or all my diamonds in my query, or my cliques. I just want to find the ones that just newly got formed once I added these 5 edges. So those types of temporal querying, continuous querying, there's a lot of work on that. So from my work, I showed you the generic join algorithm, right? We have an algorithm called delta generic join. That's, again, it was in the paper that I co-authored with Frank McSherry and Khaled Ammar, where they also got integrated into earlier versions of GraphflowDB that was able to support those types of continuous queries. So you could only get the lately formed triangles and whatnot. So there's some work in that space. And there's good sort of techniques to actually get some provable nice guarantees for such continuous queries.
Thank you so much. Perhaps the last question at high level, in these graphs, right? They are richly labeled with data. So how do you see this field of graph databases, I guess, moving forward, how does it relate to, I don't know, column stores? And yeah, I don't know, in which cases would you choose which to model your data?
Yeah, excellent. So I am quite opinionated about this, that, I think graph database management systems, they're, as I try to articulate, we should think of them as relational systems that are optimized for end-to-end joins. So it's more a question about your workload. So both columnar systems and graph databases, they're going to be good if you have analytical queries that need to read a lot of data. But graph databases are going to be more performant, you can expect, if your data has a lot of end-to-end relationships across your nodes. And so in those cases, you're going to get more performance. You should expect more performance from graph databases than columnar stores. But if you're doing traditional sort of heavy aggregation based processing, where the joins they don't grow that much, so maybe your degrees are very small, then columnar systems are quite mature too. But so our last paper that I linked is titled actually Integrating Columnar Storage and Query Processing Techniques into Graph Databases, where because those systems, the columnar systems, have been read optimized, we have taken several techniques from columnar systems and integrated them, which requires modifications because of these end-to-end join workloads that we're optimizing for. So things like execution on compressed data, or block-based processing, as I showed you. So we have essentially modifications of both storage and query processing techniques. But I do believe the core physical data layout of graph database should be columnar, but you need optimizations to make them work under end-to-end joins, many-to-many joins.
Super. And perhaps one last, can you comment a bit on kind of the overhead, kind of memory storage overhead, I guess, because you are now modeling all these edges and these relations explicitly and so on.
Yeah, so the big memory overhead actually is, there's a 2x overhead you get in graph databases by double indexing your data, because for most queries, you'll want to be able to go to a node, and because edges have directions, you will want to sometimes move forward and sometimes move backward. Certainly in every analytic systems, things are double indexed, but graph databases also do double indexing, which means which a lot of columnar systems wouldn't. Like your tables don't get double indexed by default. So there's that overhead. But there's also some compression techniques you could use to store some of these edge records very succinctly. And our last paper again talks about several compression techniques. But I haven't benchmarked, for example, a system like MonadDB, or maybe something like Umbra, which is state-of-the-art relational system nowadays. What is their memory footprint compared to ours? But we do sort of have incur this cost of both keeping pointers around for edges and double indexing. So that exists there, but it comes with huge performance gains.
Super. Thank you very much. This was an excellent talk. Very cool topic. Thank you everyone for attending. I will also tell you about the next talk. So the next speaker we are going to have is on April 22nd. It will be Ras Salakudinov, who's an assistant professor at Carnegie Mellon, doing some pioneering work on neural networks and deep learning. So hope to see you all in about 3 weeks. And thank you again, Semih. It was excellent, really engaging.
Thank you very much.
I appreciate it.
Thanks everyone for listening.
Thank you, guys. Bye-bye. Nice day.